Hello everyone, welcome back to Chem. Today we have an exciting session ahead where we'll see some important problems based on Dienone Phenol Rearrangement. If you are new here, don't forget to subscribe and hit the bell icon to stay updated with our upcoming videos. Let's jump into it. In our channel, we already discussed Dienone Phenol Rearrangement basics as well as magnetic details. As a quick recap, the Dienone Phenol Rearrangement is an interesting transformation where the dienone can be converted into the phenol in the presence of acid. Today, we are going to tackle it by solving few problems step by step. Before that, you should remember all these rules in order to solve the dienone phenol related problems step by step. Let's start with our first problem. This is the question from CSIR 2019. We have a dienone structure. I will guide you through step-by-step process in order to solve this problem. First, we will try to solve left-hand side problem. Here you see the place of R. We have ester in the presence of trifluoroacetic acid. What you will get? This is the first question. So when we use the trifluoroacetic acid, that will readily protonate our carbonyl oxygen, then followed by this electron moves towards to the oxygen, and followed by this electron moves towards to the carbonyl carbon, resulting that we will get this type of carbocation intermediate. Once if we get this carbocation intermediate, we have two possibilities: either methyl group possible to migrate or ester group also possible to migrate. So we will see one by one. If we try to migrate methyl group, we end up with this type of carbocation intermediate. And similarly, if we try to migrate ester group, we get this type of carbocation intermediate. Now we should see which carbocation intermediate is more stable. First, we see this carbocation. So this carbocation can be stabilized by methyl group. So methyl group can stabilize this carbocation by hyperconjugation as well as plus I effect. Now we move on this carbocation intermediate. This carbocation directly attached with ester group. So here you see ester contains carbonyl group. That carbonyl group has electron withdrawing power. Therefore, if you put some electron withdrawing group near to the carbocation center, that will destabilize that carbocation intermediate. So therefore, this particular carbocation intermediate is not much stable compared to this methyl attached carbocation intermediate. So therefore, we can generalize this concept. So electron withdrawing group get more preference in order to migration in the dienone phenol rearrangement. So once if we get this carbocation intermediate, then followed by fall of the H plus ion, you will get this corresponding phenolic compound. So this is the answer of A. So next we move on right side problem. So instead of R, you just put the phenyl group at same trifluoroacetic acid condition. The same thing will happen. Initially, that oxygen readily protonate by using acid, that followed by migration of this electron towards to the oxygen, then followed by this electron migrated towards to the carbonyl carbon, resulting that you will get this new carbocation intermediate. So once if you get this carbocation intermediate, you should remember this migratory aptitude we already seen in our previous videos. So phenyl group will get more priority than alkyl group. So this is really simple. You just migrate phenyl group, you will get this new carbocation intermediate, then followed by fall of the H plus ion, you will get the corresponding phenol product. So this is the answer of B. Now let's move on to the next problem. So this time we have slightly complex dienone structure. Don't worry, we will try to solve together. So when you apply the acid, here there are two possibilities. Since this cyclohexadienone is an unsymmetrical cyclohexadienone. Therefore, when you try to acid, most probably you will get the carbocation this side as well as this side. Okay. So whenever you get this type of cyclohexadienone, first you should see the electronic nature of this cyclohexadienone. Okay. Then how to see the electronic nature of cyclohexadienone? First, you should find the most electronegative atom in the cyclohexadienone framework. Absolutely, oxygen is a more electronegative element in this framework. So this is the carbonyl oxygen. Okay, so this one will get the delta negative since this oxygen pulls the electron from the near center. So for that reason, this will get delta negative. The same time, this 2 center will get slightly positive. That means delta positive because of this carbonyl oxygen. Apart from this, we should see some other groups. Here you see this is the hydroxy group. This one is attached with alkene, that means ene. So this one we can say enol. So you just, I would like to remind you, whenever you find the enol or keto form, that will readily undergo ketoenol tautomerism in the presence of acid. Okay, so when you observe this type of ketoenol tautomerism, so definitely you will get the slightly negative charge in this particular carbon. So because of this electronic nature of this particular center, when you use acid, that will selectively produce the carbocation into this corresponding this side, mean right side. So once if you get carbocation in right side, so your one of the methyl group will migrate to this carbocation center, resulting that you will get this intermediate, then followed by fall of the H plus ion, you will get this corresponding phenol compound. Next, we moving on another problem. So I would say this is one of the interesting problem because I never seen before that fourth position having chlorine atom as well as methyl group. So therefore, when you subject under the trifluoromethane sulfonic acid, what you will get? This really difficult question. Which group will migrate? Chlorine atom or methyl group? Okay, we will solve together. So when you subject under acid condition, here one more problem. Which side your carbocation will generate? Either left side or right side. Again, one more difficult situation. Okay, according to this reaction, when we use trifluoromethane sulfonic acid, selectively carbocation generated on the left side. Once if it generate this carbocation intermediate, the next step will be want to shift. Which group will migrate? Either chlorine atom or methyl group. So just like that, our previous case, when you try to migrate chlorine atom, you will end up with methyl attached carbocation. That carbocation can be stabilized by methyl group by plus I effect as well as hyperconjugation. Instead of migrating chlorine atom, if you migrate methyl group into this center, you will get one new carbocation center which directly attached with chlorine atom. So definitely now you may get some confusion because you just remember if you have carbocation near to hydroxy groups, those carbocations are stabilized by resonance since oxygen has 2 lone pair of electrons. If you think that concept, you just apply to chlorine atom because chlorine atom has 3 lone pair of electrons. So definitely one of its lone pair of electron can possible to stabilize that particular carbocation center. However, in this case, we should see one more fact. Since chlorine atom can withdraw the electrons inductively from this particular carbocation center. Therefore, this particular case, that chlorine atom inductive effect only get dominated. Therefore, chlorine atom only migrated towards to this carbocation center. If you are struggling to think this much level, you just keep remember this particular rule. So whenever you see this type of electron withdrawing or electron donating group all together in this particular center, you just apply this rule. Electron withdrawing group will get more preference than electron donating group. So now you think about this point of view, chlorine atom, one of the most electronegative element. Therefore, that will withdraw the electrons. Therefore, that chlorine atom will migrate. And similarly, now we can easily clear in this point why that carbocation generated particularly left side, why not right side? Since chlorine atom slightly bigger atom than carbon. Therefore, if you try to migrate this side, so definitely the chlorine atom may feel steric hindrance. So for that reason, the chlorine atom selectively migrate this side. So which leads to generate this carbocation intermediate, then followed by fall of the H plus ion. We will end up with this new phenol compound. This is really interesting problem, isn't it? Okay, let's move on. Another problem. Now you see we have a cyclohexa dienone. So when you subject under the acid, so here up to this level symmetrical, that means we don't have any problem to generate the carbocation either side. So one of the side, if you generate this carbocation intermediate, now we should think which group will migrate, either this oxygen attached groups or this carbon attached groups, which will get more preference. So first you see that oxygen has electron donating power through the resonance effect, since oxygen has two lone pair of electrons. And similarly, we should think about this carbon. Carbon also will donate the electron to the center by plus I effect. So again, I would like to remind you this rule. We already see in our previous video. So less electron donating group will migrate. Now you should see this one also electron donating group. Again, this one also electron donating group. So which one is the less electron donating group? Again, one more time, I would like to remind you, a resonance will get more preference than plus I effect. Therefore, this one has more electron donating power than this carbon center. Therefore, that carbon will migrate. You will get this intermediate that followed by fall of the H plus ion. You will get this ring expanded phenol as a product. So next we move on slightly somewhat complex cyclohexa dienones. When you subject under the sulfuric acid, what's the answer? That's the question. So similarly, up to this level, you see again this one of the symmetrical cyclohexa dienone up to this level. Okay, up to this level. So when you subject under acidic condition, so you will get the carbocation, this near carbocation, then followed by we should think about which group will migrate, either phenyl group or this secondary carbon. So again, once again, you should remember our migratory aptitude. So phenyl group will get the more migrating power. Therefore, that phenyl group only migrated towards this carbocation center. You will get this intermediate that followed by fall of the H plus ion. You will get the ring expanded product. So next we move on. One more interesting problem. Once again, slightly complex problem. Don't worry, we will solve together. So when you see this type of ring fused cyclohexa dienone, first rule we should see the solvent, either aqueous solvent or non-aqueous solvent. So here you look acetic anhydride, so TSOH, that means that para-toluene sulfonic acid. So completely this one is non-aqueous condition. And one more thing, you don't confuse yourself, because here they mentioned the second condition, then water. Since the first condition only the rearrangement condition, second condition is completely different. Okay, so we'll see one by one how to solve this problem. So when we use acetic anhydride and para-toluene sulfonic acid, that one readily react with cyclohexa dienone. How that will react? So initially that oxygen has lone pair of electron, so that will readily attack the acetic anhydride, so which leads to acetylation takes place. So because of that, oxygen already used its lone pair of electron to form the bonds with acetic anhydride, which leads to this electron migrated towards to the oxygen, then followed by this electron migrated towards this center. You will get this carbocation intermediate. Okay, this one is a tertiary carbocation because we are using non-aqueous reaction condition. But when you use aqueous reaction condition, you will get the secondary carbocation. So that's the difference between aqueous as well as non-aqueous reaction condition. So here, tertiary carbocation, once if you get the tertiary carbocation, what will be a next step? On to shift. So here you see this carbon-carbon bonds breaks, then followed by this carbon migrated towards to this carbocation center, which leads to a ring contraction takes place because of this bond breaking. So you will get carbocation this center. So after that, so this electron, this pi electron moves towards to this carbocation center. You will get one more new carbocation. Once if you get this new carbocation, there are two possibilities, either secondary carbon or tertiary carbon, which will migrate. Once again, I would like to remind you about our migration aptitude. So tertiary carbon will get more preference. Therefore, tertiary carbon will migrate, leads to breaking of this carbon-carbon bond, which leads to generate this new carbocation intermediate. After that, fall of the H plus ion, you will get this intermediate. Now, that next step, that water plays the crucial role to deacetylate this intermediate by hydrolysis. You will get this phenol as a product. This is really interesting example, isn't it? Let's move on. Another problem. So this is one of the very important problem, since this question asked CSIR 2013 as well as University of Hyderabad PhD entrance exam 2018 as well as GATE exam 2020. So sometimes they use H plus, or sometimes they mention sulfuric acid. So when you find sulfuric acid or H plus, absolutely this one is a aqueous reaction condition. So when you subject under the aqueous condition, what you will get? You always will get the meta product. But when you use non-aqueous reaction condition, you always end up with para product. Okay. So now we solve this problem. When you subject under the acid, that will readily protonate this carbonyl oxygen, then followed by movement of electron towards to the oxygen, as well as this electron moves towards to the carbonyl carbon, then leads to generate new secondary carbocation intermediate. So after that, 1,2 shift takes place. This methyl group migrated towards to this carbocation center. Since this one is a secondary carbocation, now this one is a tertiary carbocation. Okay. So after that, they fall off the H plus ion, you will get this product. So this one is a meta product. So this one is a hydroxy group. So here methyl placed in the meta position. Therefore, we are getting meta product. So this is really simple example. So next we move on slightly complex problem. Since we have allyl as well as fused ring in the cyclohexane dienone framework. So here this one is a allyl substituted case. So don't worry about solvent, what solvent you are using, either aqueous condition or non-aqueous condition. Here doesn't play any role in the place of allyl substituted cyclohexane dienone, because the mechanism is totally different from our previous examples. So, but initial conditions are mostly similar. So when you use acetic anhydride sulfuric acid, just like our previous case, acylation takes place and followed by generation of new carbocation, secondary carbocation. So then followed by that 1,2 migration takes place. Here you see how that 1,2 migration takes place. This electron migrated towards to this center and followed by this pi bonded electron attacks this carbocation, so which results that generation of new tertiary carbocation center, then followed by Pope rearrangement takes place. Here you see this electron moves towards to this center, then followed by this pi electron attacks here. So this pi electron moves here, then this pi electron moves towards to this carbocation center, resulting that generation of one more new carbocation. Then followed by fall of the H plus ion, you will get this product. Now that second condition will play the role. When you use sodium hydroxide in methanol, you will get deacylation takes place, you will get this one as a major product. So similarly, when we use this condition, we have one more possibilities to generate tertiary carbocation intermediate. So if you get tertiary carbocation intermediate, now that 1-2 shift takes place here to here, leads to generate one more new carbocation intermediate. Then Cope rearrangement will takes place. You will get this new carbocation intermediate that followed by fall of the H plus as well as treatment of sodium hydroxide methanol. You will get this one as a minor product. Therefore, when you use this type of fused cyclax or dienone along with allyl group, you will end up with two products. So this one is a major product and this one is a minor product. There you have it. We have solved some important problems together. I hope this session has clarified the concepts for you. If you have any questions or if there is a specific topic you would like us to cover, feel free to leave a comment below. Don't forget to give this video a thumbs up if you have found it useful. And thank you for joining us today. If you enjoyed this video, please share it with your friends and remember to subscribe for more in-depth discussion on organic chemistry. Until next time, bye-bye.